This is the first team of the class that Dr. Balgary and I are co-teaching this semester. So this is detailed, I almost said preliminary, detailed spacecraft design, and this is Team ALPS. And so I will pass it off to their team lead to take it away.
Thank you, Dr. Martin. My name is Michaela Bridges. I am the team lead for Asteroid Logging Platform Solution, better known as ALPS. My team consists of my co-lead, Ethan Creel, our treasurer in electronics, Hunter Ray, Damari Hackett, our electrical lead, Zachary Linder, our structural lead, Kyler Bruno, a part of our drill and structural teams, and Tristan Cook, our drill lead. I'll pass it off to Ethan to go more in depth about the scope of our project.
Thank you, Michaela. So as you can see, ALPS has finished assembly this semester. This includes construction and assembly of both our structural support subsystem and our attachment subsystem. We've also undergone testing, and we will serve as the M-class asteroid test bed. On the topic of M-class asteroids, which are also known as metallic asteroids due to their high metal content, they are the cornerstone and foundation of our project as they offer unique mission types. The first being research. Hardly any missions have gone to M-class asteroids, and none have landed on them. Therefore, actual information about them is extremely sparse. It's also been theorized that some could be the cores of long-lost planets. The next major mission it would offer is mining. Since they are mostly metal, it would be feasible to go out and mine common ores there. However, economically, you probably would not want to send a mission all the way out to an asteroid just to get some iron and nickel, which is where the last point comes in, where it's been theorized that they could contain extremely large deposits of rare earth elements, which are vital in semiconductors and used across almost every single industry that we have. On the topic of economics, it should be noted that ALPS has a limited budget and a limited time. Because of these limitations, we've had to downscope our project to a level that we could actually build and test something in this semester. To this end, ALPS will serve only as an Earth-based testing prototype, and it will not concern itself with actually getting up to space, operating in space, or getting to the M-class asteroid. From our main idea, we have derived the following two primary objectives. The first, that being an actual asteroid attachment. Since the core of our project is centered around asteroid attachment, it is our primary objective. This will detail ensuring our system can actually properly attach itself to our simulated M-class asteroid surface. Our last primary objective is our two-person attachment. Since ALPS was made in-house in a machine shop and needs to be transported to and from campus to our testing site and even to here, we had to ensure that it was both light enough and space small enough to ensure proper transportation. And now Zachary will detail our changes to our design.
Thank you, Ethan. So here's a brief design history of ALPS, starting with our beginning iterations. Some of the main components of ALPS include the spindle and dual leg support setup. These informed a lot of the geometry decisions we made as we were designing. The next significant portion of ALPS was the electrical subsystem. These would drive all of the dynamic components of our system, as well as optimizing the attachment system to effectively connect to our structural subsystem. A little later on, we increased the size and radius of our drills and spindle to account for a larger volume of sand and gravel. We also added leg brackets, as you can see. This was to reduce any welding, so it would increase manufacturability, and in case we made a mistake, we could always redesign and redevelop. Then, a little bit later on, we changed the drill design from conical to cylindrical. The main reason we did this was because predicting exactly what the radius would be after we press molded it was difficult, so we just resorted to doing cylindrical blades to decrease the complexity of manufacturing. And this is the final design as of the detailed design phase. The last major change we made was instead of 3 revolutions per drill blade, we just resulted to a single blade. This actually worked in our benefit, as we will talk about a little bit later. To understand exactly how our design changed before and after manufacturing, we can see the conical drills, we still had the drill and spindle motors the spindle, and then the legs. Comparing this against our current design, we changed it again to a cylindrical single-bladed drill. We also added C-channels and L brackets. These would support the position and level of all the linear actuators. We also adjusted the spindle spacing because we have a lot of rotating components. We didn't want any nuts or threaded rods or screws to hit each other as we were rotating. We also increased the scale of our linear actuators. We originally underestimated the weight of our actuating subsystem, specifically the drill motors. So increasing the torque rating of the motors was necessary for optimal performance. We also added corners to the bottom legs. This was so we didn't have to drill the screws in on an angled surface. We got a flat surface as a reference point. And then the last major change we made was we thinned the material of the flanges. We did this to reduce the weights, therefore increasing the portability, and also so we can use wire jetting as a method of creating our parts as opposed to CNC. To understand more about how our attachment system actually works, so we have the drill and motor. They are connected by a couple which friction fits it via screws. We have our spindle motor, which stays static relative to the axial motion of the actuators, and that drives the rotation of the drills. To see a little animation of how this works, so the actuators can lower and raise the actuating mechanism as needed. The spindle motor can spin the drills to a different position as needed. There are two unique drilling locations, as you can see here on the bottom, that are 90 degrees apart. Any third or fourth or fifth drilling operation would result in overlap between a previous drilling site. To understand exactly how the actuating mechanism fits within the structural subsystem, each of the three actuators is fitted with an L bracket and washer screw setup. So there are a total of 12 screws that connect the actuating mechanism to the structural subsystem. We use 3 linear actuators as opposed to 1 or 2, mainly so we have 3 points of contact, and that way we have an even distribution of upward and downward force on our attachment system. Now I'll pass it off to Damari to discuss our electronics that drive these components.
Thank you, Zachary. So for our electrical subsystem, we had a couple of issues, and okay, there we go. Sorry about that. Our first issue was with our stepper motor drivers. We could get them to work, but we couldn't get them to work all at the same time or consistently. We believe this has something to do with the current limiting potentiometer, and this just made it so that our motors didn't get too much current, just protected our motors. And then our second issue came from our IMU sensor. This was just going to give us our accelerations of our system while it was in operating mode. But again, we couldn't get this to work because there's a specific I2C address that we have to find in order to program it, but we couldn't find that after multiple attempts. So because of these issues, we couldn't do all the testing that we wanted, and therefore we couldn't verify all the requirements that we wanted. So I'll now pass it off to Michaela to talk about our driver requirements.
To shape the mission of ALPS, we have 5 driving system level requirements. The first one includes our mass, which states that the system itself should be less than 22.7 kilograms. Our next defines what we'll actually be testing on. This, as a team, we decided to be 55-45 sand gravel mixture to most mimic an M-class asteroid surface. Our next one is the axial displacement, which says the system should withstand a 40 Newton force in the axial direction without displacing more than 3 centimeters. The next one is our time constraint, which says that the system should complete a full attachment within 15 minutes. And our final one is our successful attempts, which allows for the system to make an attempt twice in succession. So for our first requirement, our mass, what we did is we took a luggage weight sensor, wrapped it around the L bracket attached to the linear actuator, lifted the system until it was completely still and completely off the ground, and took the mass that way. As you can see behind me, we did this 3 different times. It came out to be about 21 kilograms. Compared to our SolidWorks model, it being 30 kilograms. We see this discrepancy most likely due to the way we modeled the actual system. Our motors in SolidWorks were completely solid. and the actuators weren't the correct dimensions compared to our actual real-life actuators. So this is most likely due to the discrepancies that we're seeing between the masses. Our next requirement is our test surface. So in order to control how we were modeling our surface, we did it in layers. So as you can see behind me, we alternated between sand and gravel, one layer being a complete mix and the topmost layer being a hydrated sand layer. Behind me, you can see that the surface was about 7.5 inches, and this is where we estimated our drill fell during testing. So we took a Home Depot bucket and marked it. This allowed us to control the amount of material going into our test surface so we can model it the most accurate way. We also, to increase the cohesive properties of the material, we decided to mix it. That way it would be more in our benefit when we were drilling down and we would be able to make a more secure attachment. I'll now pass it off to Tristan to go over the axial displacement requirement.
Thank you, Michaela. Okay, so you can see here, because of our electrical issues, we resorted to hand drilling our, our auger drills into the surface. So what we did is we spaced them out 6.5 inches so that when we actually attached the ALPS model onto it, it would fit. We had to hand drill because we couldn't actually actuate them down. Once we attached the ALPS model on top of the drills, we then attached the suitcase weight sensor onto it so we could set up the ALPS model for its actual loading test. You can see here we are lifting out the model once it's been attached. This reading is in pounds. We subtracted the actual weight of ALPS and then converted that into newtons so we could see the actual axial force we're receiving. We needed to be larger than 40 units to pass this requirement. Each time that we ran it, we were significantly larger, so we verified this requirement through that way. Next, I will pass it to Tyler so he can talk about the time constraints.
Thank you, Tristan. Next up, our next major requirement is our time constraint requirement. This requirement states that we have to complete an attachment within 15 minutes. We were unable to test and verify this requirement due to our previously mentioned electrical issues. However, we are confident that the torque and speed our linear actuators would operate at would be able to complete an attachment in 15 minutes. Next, our next requirement is the spindle of the successful attempts requirement. This requirement states that we have to attach twice in succession without resetting our test surface. However, we were unable to do that because of our electronic issues as well. However, when our electronics were working, here are a couple videos. We have our spindle motor moving the drill positions of our attachment system, and then another video of our auger drills attached to the spindle as well, moving the locations as well. We believe if given more time, we would have been able to figure out our electrical issues and complete this verification as well. That concludes the 5 driving requirements of ALPS. We were able to verify 3 out of the 5 requirements. The first one being the system mass, the second one being the test surface, and the third one being the axial displacement. Okay. We were unable to test or verify the remaining 2, the time constraint and the successful attempts. Furthermore, ALPS can be broken down into 2 major subsystems, the electrical subsystem and then the structural subsystem. Now I'll pass it off to Damari to talk about the electrical subsystem.
Thank you, Tyler. Okay, so for our electrical system, we have 2 driving requirements. The first being our electrical capability, which just says that we must use electronics to operate our system. The second being our power integrity, which just says our electronics have to be powered while in operating mode. So a deeper dive into our electrical subsystem, we have our IMU sensor, the Raspberry Pi Pico. This is where we'll upload all of our software and control the rest of our electronics. Next, we have our stepper motor drivers, which again are just used to control our motors and take signals from the Raspberry Pi. And lastly, we have our IMU sensor, which is giving us our accelerations while we are in operating mode. And then there's our actual electrical subsystem. And as you guys can see, we did use electronics, so we did pass our electrical capability. And then for our power integrity, again, due to our electrical issues, we were only able to verify this for 2 of our motors by the time testing came around. All of our motors run at 24 volts, and the ones that we were able to test were using 0.66 amps and 0.8 amps while in operating mode. So all in all, we were able to verify our electrical capability requirement, and we did not meet our power integrity requirement. I'll now give it to Hunter to talk about our structural subsystem.
Thank you, Maureen. So our structural subsystem is comprised of 3 identical parts, and those we call structural thirds. These consist of our feet, the legs, and then these connecting flanges that are then screwed into the linear actuators. We decided to break it up like this to ease the manufacturing process. As you can see here, Tyler's holding our first one, while the rest of the team was able to work on constructing the other 2. With these all screwed into the sides of the linear actuators, these make up our entire structural subsystem. The couple of driving requirements that we had for this subsystem, first was that we had to have a mass of under 20 kilograms, and also we had to have a structural yield which stated that we must have 0 plastic deformation visible of our system after testing. To talk about our first one, our structural mass, we had first uploaded our system into SolidWorks Applied Steel and found our weight to be about 19.5 kilograms. This was also, like Michaela mentioned, from having our linear actuators be solid steel. And then we completed the same test that we did with the full system by strapping our luggage suitcase weight around the entire, all the flanges, and then getting our weight to be about 12.75 kilograms. For our structural yield requirement, we had uploaded our system into ANSYS and applied the same forces that we would see during our testing. So here in this picture, we can see that the linear actuators are pulling all the force because that is where the stress would be seen, which was at 40 newtons. And then our feet were fixed so that it would simulate being on the surface. On the left here, we can see all the values from our deformation. The lowest one on the bottom half, we can see that that is where the most deformation would happen. These values are in inches, so the most deformation would occur at about thousandths of an inch, which we deemed would not show any actual plastic deformation. So for our structural system, we had a weight of 12.75 kilograms, which is under the required 20. However, we were not able to verify our structural yield system because we did not do the proper testing due to the electrical issues that we have. But we do believe that it would have survived all the testing we would do, because after doing our pulling test and transporting this in the back of my car to other places with my driving, it survived. So yeah, since then we have still not seen any plastic deformation, and we believe that it would survive any other tests that we would have to do. Now, Ethan will talk about the things that we've learned over the years.
Thank you, Hunter. So, over the course of this design semester, ALPS has learned quite a few important lessons. The first being teamwork. Since our entire group has been working in the machine shop, bringing other documents, interacting with each other, interacting with the machinists, we've interacted a ton in a team environment. We've really learned the importance of being able to successfully work with each other. The next major lesson that we learned over this semester was on time management. Initially, the main lesson here is the importance of accounting for things that we didn't really see coming. As, for example, the machine shop accidentally misplaced one of our orders for around a month, which added quite a few, some time to our overall project. And our initial plan, our initial schedule for this semester also didn't account for our design changes, or even all the out-of-class stuff that we had to work on, and other classes that we also had. The next major lesson we learned was on technical writing. This is mainly on our verification plan, which is the document that actually specified how we were going to test all of our requirements to actually verify them. The next major lesson we learned was also on project scoping. While most of our downscoping occurred during prelim last semester, we still downscoped our project a little bit during manufacturing, mainly in regards to our electrical system as we had problems with it. So we essentially just downscoped how many rotations the spindle would actually be able to perform in order to try and get it to work. That's strange. So our next major lesson that we learned was actually on project manufacturing, as this semester is all about actually building our project. And since our project is all steel, all those components other than the drills and linear actuators and the electrics were actually manufactured in our machine shop. Some of the parts were sent as work orders for our machinists, others were made by us on the various machines. We learned a lot about actual machining, and the main lesson here is the importance of picking the right machine for the correct job, as we spent around a week using a drill press to press holes into our flanges and support brackets, only to find that this was not accurate enough. Once we actually tried to put our entire structural system together, the holes did not line up with the screws. This caused us to have to go to one of the mills to actually machine out those holes, and this probably added a month of time, as the mills that we have on campus and the machine shop are under high demand, and we had to spend most of our time waiting to use that. And the final lesson we learned was on actual part drafting. This mainly relates to those machine shop work orders, as we had to submit quite a few of them with all of our parts properly drafted. The main lesson here was the importance of actual part tolerancing, as some of our parts would have either too high of a tolerance for the needed application or too low, or in the best case of this, our original spindle idea was a full half an inch thick of steel, which would be extremely hard to machine in our in-campus machine shop, and would also add quite a lot to construction time and material cost. And now Michaela will conclude our presentation.
As we conclude, I would first like to give a few special thank yous. Our first one being to our lovely professors, Dr. Martin and Dr. Belvery. They have seen our project from the very beginning to the very end, and they've done a great deal of work with us. My next thank you goes to the other faculty on this campus. Dr. McNeil and Joseph Chandler were a great help in problem solving some of our electrical issues. Dr. Madler and Professor Benton helped us narrow our scope and actually choose our attachment system. And Mr. John Kelly helped manufacture our drill and gave us some effective advice on manufacturing. I would also like to give a special thank you for Cruciate Steel for supplying a lot of our material, and also to the machinists Patrick and Scott who helped us along the way. Even with issues that occurred, we believe that if given more time, we would be able to create a successful system. And with that, any questions?
So we will start with questions from the audience, and then we will also take questions online on Zoom. So it looks like we've got a hand already, Joseph.
I understand you had to use DeWalt to help you get the drills into place. Did you characterize the torque of the DeWalt drill to the motors that you have on there so that you would have comparison?
Yeah, so the motors that we're using do have kind of a curve or graph which has the torque related to the rotations per minute. So we did try and kind of calibrate that with the drill that we used to actually drill it and do our actual testing.
Was that similar?
Yeah, we tried to get as close as possible. Good job.
Did y'all take into consideration if this is actually on an asteroid, what will you need to do any dust mitigation for what you will probably be throwing up with your drills?
Yeah, we thought about that, but for this circumstance, we decided to ignore it because dust would fly up into their system.
Understandable.
I see that you guys were doing a mix of sand and open rock pebbles, but a lot of M-class asteroids are actually solid core. So have you guys thought about, this was an asteroid, how you'd stay mounted while you're trying to drill, and then also the thermal effects of all that heating up while you're drilling into hard rock?
Well, so we were just looking at the surface regolith layers for the M+ asteroids, because like you mentioned, they have a solid core, but that's not the surface that you've seen before, so that's why we think sand and gravel. But in terms of the thermal effects, because we're just making like a prototype for testing here on Earth, having thermal radiators and ways to radiate off that thermal radiation would have been out of scope for something that we can do in this.
Awesome. And my last question for you guys would be, why is there a timing requirement? If you're assuming that you're going all the way to an asteroid, why does it matter if it's drilling within 15 minutes or not?
The timing requirement was more for our testing itself, just to make sure we weren't spending all day waiting for our drills to go to the surface. It was for us to make the call, okay, it's not working, what's the next step do we need to make?
All right, I've got a handful, but I'll pick a few. First thing, I2C steppers. They're a challenge, and I've dealt with them my whole career, and they are hard. So I understand you guys' struggles there. Don't be afraid to ask for help. Is my biggest piece of advice there. I'm not sure what professors are still around, but you guys have a lot of experience available to you, and I would suggest reaching out to them. It's always good to network and know people. Why did you use a Raspberry Pi instead of something like an Arduino?
I think I just had more personal experience with it. I was more comfortable with it, and our software wasn't very difficult to just fit in some stepper motors. So yeah, it was cheap on Amazon. So that's it.
It's valid.
Yeah.
My other question is, if I had to pick one, I'm going to go with I guess they're one and the same failure modes. Have you guys considered what would happen if one of the motors on the lifting mechanism were to fail?
It would just fail.
Okay, because my question was, I know you guys had the concern of the weight problem. I've worked in the space industry for a number of years, and redundancy is always one of those things that comes and bites you. So that's why I was curious. Same thing with the actual motors that actually do the drilling. If one of the motors fails, you can't actually continue the mission. So that was something that comes to mind. I'm not quite sure. You'd have to figure it out amongst yourselves how you would solve that problem. But those are things to consider when you have essentially autonomous missions like that. Is what are the modes of failure that you're going to experience, and how can you potentially mitigate them?
These linear actuators are actually rated for 10 kilograms going up and down. So we believe even if one failed, the other two might be able to push the other one down, but we haven't tested that.
Yeah, usually screws don't like doing that. I guess I'll do one more, just for fun, because I'm curious. In your backup slides, I see that you have an ANSYS analysis for the torque on the actual drill itself. I think it's slide 56.
Yep.
Okay, so what would be nice in this case is to see more of like almost like an isometric view of the torque through the shaft, rather than just on the blades themselves, because the blades won't experience too much of that torque, but that shaft will. And I'm curious if you guys were able to test it, if you were able to test it, how those couplers are attached to the shaft. If they're only set screws, they have a high likelihood of slipping. Keys or pins might be an option that's a little bit more secure, just for things, if you have, if things aren't ever perfectly aligned, like you had problems with, putting bolts together, drilling by hand, mechanical tolerances always are there, So one of the things that, if you had to choose, that would be something I would test for, if you had the capability to.
Yeah, the motor shafts were keyed. We also flattened one of the sides of the drills that we wouldn't have any slippage. But yeah, we didn't really see a torque we were using as super like high to limit to result in any slippage, but yeah, we did add like a standard key on the shaft to make sure.
Okay, good.
Yeah.
Yeah, just make sure you're not putting, set screws on round shafts.
Yeah.
Good.
So, the first question is that IMU you mentioned, what was the purpose of the IMU? If you got it to work, what would it be doing for you?
Thanks to Mark.
So we just wanted to see the accelerations that our system was experiencing while drilling, because on an M-class asteroid, the acceleration due to gravity is very low. So the friction on our feet between the surface of the asteroid and our system would also be very low. So one of our concerns was that while it was drilling, the whole system would be moving too much or like spinning, just doing things we don't want. So we wanted to monitor how our system was moving while it was actually drilling.
Alright, so it's instrumentation more than critical to like the actual drill?
Yeah, no,
Okay, cool, just making sure, so if that didn't work, but the separate motors did, you still would have been able to?
Yeah, we still would have done a lot of our tests, but one of our requirements would have been failed because one of our requirements was that we could not move 3 centimeters from our original position.
And then a more generic question, you mentioned your time management was difficult and you didn't have accounting for things. If you had to do a project of roughly this scope again, how would you have done it? Did that part of it differently? Schedules, cycles, that kind of thing? Anyone?
I think we were very optimistic about what we could have done in the future. A lot of us didn't have machine shop experience, and there were a lot of capstones this semester. I think if we were to do this differently, we should have been more, not less detail oriented, but all of us jumped in on the problem, which I think was good in the moment, but I think it ended up hurting us when we were taking in the time management portion. We got a lot of great ideas for problem solving, but we weren't able to move as fast as we should have. So I think that would be the biggest thing of probably breaking up more into sub-teams, less subsystems, and working on different parts and trying to overcome those problems within those mini teams.
More of a sort of conceptual and like design system. Sorry, we may have handled this during the prelim phase, but why 2 drill bits instead of 1?
Hi, so the main reason we chose that is because we have the left and right drill, they spin in the opposite directions. Because in space, there's nothing to stop someone from spinning. We wanted to mitigate the overall angular momentum on the system by having one spin one way, one spin the other way, so there'd be like a net zero of it.
Got it, okay.
First off, just great job. I also in my capstone had my electrical system failed, so appreciate you working through that adversity and like finding different verification paths to make it work. One question along the lines of, you did the drill bit test. Did you do one where if you're canted over, if you have a similar set of inputs?
So we didn't really insert the drills at an angle. I mean, they were slightly angled because we were doing it by hand. But we did run a few tests where we had a force pulled actually and in the transverse direction, so we could apply random forces to see how it would shift. Based on if it was at an angle, we assumed that we could just drill straight in and then apply the force at an actual angle to make this.
And then electrical kind of pathway. I noticed in your video where it rotated 90 degrees, there was a bundle of wire hanging out. Any concerns there, or what drove you to leave it hanging there?
The main concern there was, so that's why we chose 90 degrees as to how far we're going to rotate it. Because like originally we were thinking we could rotate it all the way around forever, but wire management sucks, so that's why we stuck it at 90.
Thank you so much, great job.
Good job. I just had a quick question. What did your budget look like for the project?
So we had $1450 for our budget, and we spent a total of $14 buying every component, including all of our testing equipment and any safety equipment that we needed, along with the 3D filament for our drill presses.
Thank you.
So we have a few questions from online. The first one is from Jake. How did your team manufacture the drills? Thanks, Jake.
Okay, so we 3D printed a mold, and we put a plate in the mold and hydraulic pressed it to get the shape that we wanted.
Sits in there, pegs fit in. Okay, right. The idea is that this starts out flat.
Hold on, Tristan.
Oh, I need a mic.
There's people online, they can't
Oh,
hear
it's
you. I know.
Hi, so long story short, we 3D printed these molds at 40% infill. We had a flat plate that sits in the middle. We had a hydraulic actuator pushed down on it. These molds are actually larger than they need to be because steel is in elastic material. So we stretched it further than it needed to be so it would spring back into what we actually wanted.
Thank you. And then we have another question online from Austin. If one of the goals for the project is research and possible resource extraction, how do you plan on collecting materials from M-class asteroids? They also noted that you did a good job in the presentation.
So our project is strictly to attach to the asteroid, and a theoretical payload would be the one extracting, using any, like a robotic arm or a drill, and our system would just keep it in place so that their drill or robotic arm wouldn't send the project flying.
Yeah, so from that, the original, like our name being Asteroid Locking Platform, the idea was to have a system on the top that then another company would put whatever they wanted to put on top, such as their research equipment, a mining rig, or anything that they wanted to use.
Thanks. If there are any more questions online, if you want to unmute yourself or ask, or otherwise we'll see if there's any other questions from the in-person audience. Oh, there's one way in the of course.
I passed you in STEM when I was supposed to talk. Sorry, I had no idea you had to run all the way to Walmart and back. So the question I had, well, one observation is it was not a Raspberry Pi. It was actually a Raspberry Pi Pico, which was the question in front. So it was an Arduino class microcontroller, not a microcomputer. When you did the pull test, I was curious because the ground surface was really smooth, minus a hand pinch or two, which meant it looked like it might have gotten tapped down. Do we have a hand on it that can push this stuff down and make it hold better? I don't know if you understand. I would expect the surface to be rougher once it is.
When we were hand drilling, because the way we had to hold it, the drill would walk a lot. So we had to, in order to get it into the 6.5 inches, in order to fit into the ALPS, we had to move it around a bit, pack it down just so that we couldn't, we can actually attach it. However, we have a test with just singular drills without any padded down up here. I'll play a video. To see the difference, and they're pretty much the same. However, if you compacted the surface before you drilled in, we found that we would get better numbers, better forces.
Nice. So you did all the tests. That's cool.
Any other questions from the audience or online? Walk all the way back over here. Not seeing any more online, so I think we will thank you, ALPS, for an amazing presentation.